Good afternoon, everybody. Today, we will begin a new topic. This new topic is called energy. And along with energy, we will talk about work. I know in some of the textbooks that work is talked about first, and it's talked about in terms of sort of standalone section, a chapter than energy. But I think it's better to view them as a cohesive system. So we talk about energy first, and then later we talk about energy transfers, and we will talk about work because work is responsible for the energy transfer. Okay, so energy is not a unfamiliar word, right? So we talk about energy all the time in our daily lives. So I would like for anybody to name a few type of energy, give some examples. What kind of energy do you think we can see in our daily lives? Yeah, solar energy. And you have kinetic energy, very good. As you probably already read your book, right? Potential energy, right? We also, when we use electricity, that's a type of energy, right? And that is responsible for when light bulbs, you're radiating, you use electricity at the same time you give out light. Energy is giving in the form of light radiation. Of course, you have heat transfer, that's energy. Nuclear powers, nuclear energy, thermal energy. Very good, excellent. Those are all great examples that you gave me. So energy is so related to our everyday life, right? The Earth cannot operate without getting the energy from the sun, and we use batteries. That's chemical energy stored in our batteries that will be transformed into electricity. Also, we live on food and water, and we always talk about calculating. If you're talking about calculating weight loss or weight gain, you have to think about in terms of energy, how much calories you want to get in, how much do you burning, right? So with energy conservation, which is one of the most fundamental laws of nature, tell you that if you burn more energy than you eat, then for sure you will lose weight, right? That's just a law of nature, conservation of energy. So let's before we talk about different specific format of the energy we are going to discuss in this class, I want to mention a physicist and talk a little bit about how this person, Richard Feynman, defines what energy is. How does he talk about energy? I think he is really worth mentioning because he is one of the best known scientists in the world, and he's a professor at Caltech. He once even came to Cal Poly and gave a seminar and colloquium at Cal Poly. But he is very quirky. Like he kept it a secret. He asked the student not to tell any of the administrations, so he only gave it to the physics students. Yeah, nobody, even the faculty, didn't find out until he already came and left. So he has some of the language he used to describe energy. Now let's take a look at what he said. He says, it is very important to realize that in physics today, we have no knowledge what energy is. Now you may wonder, if you don't even know what energy is, why we're teaching it. We further elaborate. What we mean by we don't know what it is energy is a numerical quantity, and that numerical quantity does not change when something happens. I will talk a little bit more about elaborate what that means in the next slides here. He also jokes about that all the different units that the physicists or people in other fields use for energy, for those who want some proof that physicists are human, the proof is that in the idiocy of all the different units that they use for measuring energy. Of course, it's not idiocy. He's really just joking about it, because if you look at all these different examples, are examples of units for energy. Some of these you probably have seen, like Newton times meter is what we will see in here, joules. Well, we will use those two in 1510. Electron volts, you probably see that in 1520 later on. And then food calories, right? You have the big calorie, little calories, the ones that's labeled on your food packet is a big calorie. And you look at your electricity bill, it has energy unit in terms of kilowatts times hour, like how much power you're using and for how long. The different choice of units are really just for make sense to use different units and different measurement, different energy scale. And he continue to talk about what does that mean? We don't know what energy is. So there is a law governing all natural phenomena that is called the conservation of energy. So when someone said energy is not conserved, this language gets used a lot by people who are or even not professors, or even professors use the language energy is not conserved. But what they really mean is that energy does not remain constant during the process. You have some energy transferred out of the system, because energy precisely is always conserved because of the conservation of energy. And what does this law tell us? This law states that there is a certain quantity, and we call it energy. And this quantity does not change when something happens, when the physics process undergoes or a chemical process. That is the most abstract idea because it is a mathematical principle. For example, later on we will see energy for potential energy, right? MGH. Energy for kinetic energy, 1/2 mv squared. So it is exactly these combination, 1/2 times m times v squared. This particular combination does not change when something happens. It's not a description of a mechanism or something concrete. And we calculate, okay, how much energy you have using these numbers, and you calculate how much energy you have using the same common numbers at the end of the process, and you get the same number. The energy remain the same. So it's not like we have a picture, energy comes in little blobs, little by little, cubicles. It's not like comes a little definite amount. It's just a really abstract thing. And that for that reason, we say we don't know what energy is. It does not tell us the mechanism or the reason for the various formulas. The formula is just, if we use that formula, we realize it based the law of conservation of energy. Okay, that is just a little side note of what Richard Feynman said about energy. Let's look at all the types of energy we are going to deal with in 1510. As you have already mentioned, one of them is kinetic energy, simply the energy associated with motion, right? And that is in the format of 1/2 mass times velocity squared. And we call it kinetic energy, KE. So looking at this formula, can we figure out the units for kinetic energy? So 1/2 is a constant, which is unitless, doesn't have any unit. Now we need to figure out the energy unit for kinetic energy. We simply need to look at the energy for mass and velocity squared, right? So if we put that in, if you use kilograms for the mass, if you use meters per second for the velocity, you get your units as kilograms times meter squared over second square. And yes, and we call that is exactly 1 joule for in the SI unit, standard units, 1 joule. Okay. So, so you can see that the faster something moves, V is bigger, then you need more kinetic energy. Also, if a more massive object moves, you have a bigger mass, you need more kinetic energy. All right, so let's quickly do this, answer this question. I simply tell you car A and car B, and each of them has this mass and they have a different speed. Which of these statements is true? Try not to plug in numbers and calculate. I don't think this requires calculation. Just look at these numbers and what do you think the kinetic energy between A and B is? You can go ahead and vote. Again, recall kinetic energy is 1/2 mv squared. All right, 10 more seconds. Okay, all right, let's close this and let's take a look at this together, what your results are. Okay, so here is our result. Majority vote for D. Next is E. So D says the kinetic energy of B is twice as much of A. So let's see, they have the same mass, right? A and B have the same mass. And the velocity of B is 60, whereas the velocity of A is 30. So velocity B is double the velocity of A. Does that mean the kinetic energy of B is double the kinetic energy of A? Is that correct?
No.
No.
But no. So how much should it be?
4 times because it's squared.
Yes, very good. But be careful. This is a squared, right? So if you do VB squared, VA squared is 4 times VA squared. So you have to be mindful of that. Correct answer is E. It's 4 times that of A. Okay. So the next type of energy we're going to discuss is called gravitational potential energy. There are 2 types of potential energy we will do in 1510. One is the gravitational potential. The second one come up later is elastic potential energy. So potential energy is always associated with a system involving more than one object. So here for gravitational potential energy, it's the energy associated with the gravitational interaction between the Earth, here we are on the Earth, and the object. So a lot of times we don't say this explicitly, but you should always know that if, for example, if you have this rock at a height above the ground, so you can think of this as the potential energy stored in the rock, meaning that if the rock falls, it's going to have some kinetic energy at the end, or it has the potential to do some damage when it falls. So there's some energy associated and stored in it. And it's stored not just in the rock, it's really stored in the Earth and rock system. It belongs to both of them. Because without the Earth, the rock cannot have that potential energy. It has to be the whole entire system. So a lot of times people sort of to take a shortcut saying, oh, what is the potential energy of the rock? But you know it's really the rock and Earth system, even though that you don't always say it out loud. So for the rock, for example, is at a distance h above the ground level, then the potential energy stored in the system is the mass of the rock times g, little g, the gravitational acceleration times its height. The height, where do you measure the height? That is where we define the reference point for your zero potential energy. This reference point is arbitrary. You don't have to set at the ground level. You can set it wherever you want, but throughout the problem, you just need to be consistent. So for example, within a problem, you can say, I'm gonna set the ground level to be where I measure the height from. So the rock is 20 meters above the ground, for example, and be consistent. Or another problem, say I'm gonna set it at sea level to be where I wanna measure the height. That is all okay. But you need to be consistent in the same problem. So let's look at the energy units for potential energy, like what we did previously. The potential energy will have the unit of for mass is kilograms, right? For G, it's acceleration. Meters per second square is your unit for acceleration. And you have height, that is another meter. So again, you get kilograms, meter square, second square, just the same you got before, right? For 1/2 mv squared. And that is also with 1 joule. So it makes sense because they're all energies, and it makes sense they all share the same unit, right? We sometimes combine kinetic energy and potential energy together, and we refer that to mechanical energy. Okay, that means those two of them together. So quickly, let's practice the idea of potential energy. Okay, potential energy, gravitational potential energy is mgh. Okay, so here's a question. Someone drove from somewhere in Colorado where it's 1,500 meters above sea level to somewhere in California where it's only 500 meters above sea level. How does his or her potential energy change during this process? We can assume the person's mass 50 kilo, and we can use G as 10 meters per second square. So how much does it change? The change is always the potential energy at the final location minus the initial location or initial state. Okay, so it's what you end up with minus what you had previously. Okay, and again, m joule mega means 10 to the power of 6. So this means 10 to the power of 6 joules. So 1 mj is 10 to the 6 joules. Okay, so with that information, I'm gonna let you guys vote on this. You want to use a calculator? I think for this one, you can use a calculator. Okay, let's go for another 15 seconds. So you haven't voted, please put in your vote now. Okay, all right, let's take a look. I'm gonna go ahead and stop it now, okay? All right, so obviously we could plug in numbers, right? M and G and H, different height, and simply calculate it. Or you could look at this, eyeball it, and eliminate some of the wrong answers. For example, the change would be the final minus the initial. Do you think going from a higher place above sea level to a lower place at above sea level, do you think our potential energy increased or decreased during the process?
Decreased.
Yeah, so decreased. So we should be looking at a negative number, right? If you're looking at the change from what you had later minus what you have earlier. So it would be decreased. So mgh final minus mgh initial. And a lot of times we say it doesn't really matter where you define to be your reference point. So for example, in this case, you can measure your height from sea level, or you can measure your height somewhere else. But what really matters is the change is remaining the same, right? You have lowered your height. So, so the final height minus initial height is 1,000 meters, right? So it will be your 50 kilos times 10 times 1,000 meters, right? To the power of 3 meters. So you can see that is 5 times 10 to the power of 5 joules, right? And that is, I'm sorry, negative 1,000. It's negative 0.5 times 10 to the power of 6 joules, and that is negative half of megajoule. That's B, right? So the majority of the answer you guys chose is correct. Okay. Another type. Now let's go to another type of the potential that's called elastic potential. So when you have a spring or a rubber band, then there's energy stored in it, obviously, right? Because if you let go of the rubber band, you can see that energy will be released, launch something. So give that something some kinetic energy. So there are obviously some energy stored when you push a spring or when you stretch a spring or a rubber band. So that is associated with the spring interaction between two objects. So now, for example, if you're launching a rocket, if you're launching this bird, the energy is belonging to the bird and spring system. It's not just one object. So this entire system has the potential of elastic energy. We just call it P, S as in spring. So this potential energy is calculated, right? We said we have all these abstract formulas. So the formula for potential energy stored in the spring is 1/2 times K, the spring constant, and how much the spring is being stretched, that is delta X. So which makes sense to think if you have a spring that is really strong, right, then it will store more energy with a bigger spring constant. Or if you stretch the spring by a bigger amount, you have a bigger delta X, that's giving you a bigger, more energy as well. So let's look at what are the units for this. Then you might wonder, you might say, oh, I know it's just joules, right? You're right, it should be because it's still energy. Let's see what will happen if we take the units from the right-hand side. So the energy here, units here for the spring, elastic spring, would be the energy units for spring constant K times delta X squared. Well, I know delta X is just meters, right? How much you stretch it. So this is meter squared. What are the units for spring constant? Would anybody like to tell us?
Kilogram over second squared.
Yes. And how do you know? You assume that you know this is joules. You set it to equal to what we had, but we're doing the other way around. Like we are figuring out what this will give me and compare it what we had before. Is there something other? Is there any formula we had previously that involves K in it? Because when we don't know the units for one thing, we can relate it to something else. Where might we have talked about energy for spring constant or used the spring constant in any formula?
For force.
Yeah, Hooke's law, yes. Hooke's law says the spring force is always opposite to the direction of your displacement and proportional to spring constant, right? So spring constant will be the unit for force divided by the unit for delta x. The unit for the force is newtons, right? The unit for delta x is meters, so Newton over meter. You can see when we put it together, it gives us Newton times meter. Is it the same as what we had? Is this the same as what we had previously? Remember, we got kilograms, meter square, second square?
Yes.
And why is that?
Newton is kilogram times meter per or divided by second squared.
Yes, very good. Again, these are all related, right? Newtons are, think about F equals ma. Force newtons is kilo times meter per second square, right? So if you replace this newtons using that, this is exactly the same. But Newton times meter also is revealing something more fundamental. Where we talk about work, we will talk about it in terms of Newton times meters. So it's applying force over some distance. So we will go back and refer this to Newton meters when we talk about work. But here, they're all going to equal to just 1 joule. Okay, again, a quick practice on the elastic spring. Potential energy stored in the spring is 1/2 K delta x squared. So if I have a spring here horizontally and I attach the box to it, and I let it oscillate back and forth between x and y, at point x, when the spring is fully compressed, which of these values will reach maximum? I will let you guys actually discuss this for a couple minutes within your group. You can take a screenshot before I open the breakout rooms, okay? Okay. 5 more seconds. If you haven't put in your vote, please do so. All right, I'm gonna go ahead and close this and we can take a look. All right, it seems like we all agree at least the elastic potential energy of the spring will be at the maximum. And now the question is whether the acceleration is also the maximum or not, right? So that's the difference between choice B and E. All right, so we have this formula here for the spring, and you can see that at point X, it's mostly fully compressed. So the delta X is maximum, right? At this location. So I agree here, the spring would be at the maximum value for potential energy. The magnitude of the block's acceleration. So to look at the block, right, the normal force and gravity, they cancel out. We only need to worry about the forces in the horizontal direction. So what is the force that's acting on the block in the horizontal direction? What do you think?
The spring force?
Yeah, the spring force. So at point X, when the spring is very much compressed, that's point X, the spring is compressed. So the spring would provide a force pushing on the block, pushing it to the right, right? So, and remember, according to Hooke's law, we just said this force is actually proportional to how much you compress or stretch the spring, right? So at this point, the delta X makes your spring force, potential energy a maximum. It's also going to make your spring force a maximum, right? So spring force is the maximum at this point, which means the acceleration is force over mass is also maximum at this point. So both of these would actually be at its maximum value. Okay, so it will be E. B and C are both correct. Okay, all right. So we have 3 different energies under our belt. We know how to calculate them. There are a lot of problems we can solve already. And we're going to use a conservation of energy to solve a lot of problems. And it's a very elegant and nice approach because some of the problems earlier, you can do Newton's laws, but you can also do it using energy. A lot of times when you can use energy, it's much simpler and quicker to solve those problems. So as I said previously, emphasizing conservation, it's a little bit different from what we colloquial when we say conserve something. When we say we conserve something, we just say let's not use it too quickly. But conservation of energy, meaning in physics, is that the total amount of energy in the universe always stay the same. Here we say the universe because that's the biggest system you can evaluate. The choice of the system a lot of times is up to you, right? If you choose to evaluate, let's say you, there's a lot of stuff in the room. You can choose, okay, I'm gonna evaluate my system to be simply just the desk, nothing else. Okay, then there's some kind of energy associated with it. But if you're including another desk in the room or also the floor, also some other appliances in the room, then you're making your system bigger. So depending on what you include in your system, meaning that is what you're interested in to analyzing the energy, you're gonna have different values for what the energy is. But if we're looking at the universe, you have included everything, then the total amount of energy will always stay the same. Doesn't mean that it will not transform. As energy can be transferred from one system to another or transformed from one form to another. It cannot be created or destroyed. So when I say when you transfer energy from one system to another, it's like you take money from your left pocket and put in your right pocket, right? Or you can say I take money from my checking account and put into the savings. Or even if you take money from your pocket and give it to someone else, if you consider the system to be both of you, then it still remains a constant. It remains unchanged. Now, energy can also transform from one form to another. That's like you transform your money, you trade it into buying a bike. So it's still in the form of something, it's just not in the form of money anymore. So the same goes for energy. So conservation of energy, I have this diagram to show what it represents. You have a system right here, and it interacts with the environment. So that means if your system has some initial state, some kind of energy stored, but then it's constantly changing, right? You have some final energy in the system. During the process, there energy input, energy coming into your system, and you have energy output. The system put energy away into the system. So all of that will change the energy of the system. Simply conservation is simply saying, yes, if you have a change in your energy in your system, so E as in energy final minus energy initial. So if you have a change in your energy, that means that part change can be accounted for by looking at the energy transfers. So the change always equal to how much you put in minus how much you put out. Now, I think then you might wonder, of course it is, and it is indeed, of course it is conservation of energy. If you have a change that must be coming from somewhere or went somewhere, it has to be accounted for. You cannot have this part of energy simply disappeared, right? You can always explain that change. So a very good analogy and easy for people to understand is to, again, make an analogy with the money in your bank account. And I think that helps us remembering the equation for conservation of energy. Now, of course, this is not physics. This slide is really just, I made up this slide to help us understand. So let's say you have a system that is your bank account. You try to evaluate the money at the final state minus the money at the initial state. If you end up having more than you had before, then you must put money in, right? You must have an input. Now, sometimes you take money out, that's your output. So whatever change in your account can be accounted by how much you put in minus how much you take out. Let's look at an example. And that process is exactly what we're going to do when we solve energy problems. So example with money, let's say you look at your bank account and there are 5,000 stored in it on March 1st. During the first month of March, you deposit $500 in check and you paid $400 credit card bills. On the 30th of March, you see that the bank account has $5,100 in the account. Okay, the very first thing is to be very clear about what is the system, because that might change what your energy is. Here, the system is, of course, is your bank account, my bank account. And the start state is, okay, when are you looking at? You need a process. When do you wish to evaluate? Is March 1st? And the state after is the end of the month, March 30th. So how much money you have at the start state on March 1st? It tells us it's 5,000 in it. How much money you have at the end state, final state? It says it has 5,100 in it. And how much you put in is the 500 you deposit it. How much you put out is the 400 you take to pay your credit card bills. Now you can see that you have this money conservation equation. The money final is 5,100 minus money initial, which is 5,000. There is $100 of change, right? And that can be accounted by how much you put in, which is 500, minus how much you take out, which is 400, which is 100. So the 100 is exactly accounted for. And that's what we mean by conservation. And you can think, well, of course, that has to be the way it is. And it's the same way with conservation of energy. We're going to use this equation to solve all our energy problems. And I understand it may be a little bit different than if you pick up a different textbook or if you Google online, they will have work energy theorem. But I think this is much more universal than the other things you might have seen. Because if you use the other way, they always keep track of, okay, do you have a conservative force or do you not have a conservative force? It can be very confusing. But if you use conservation of energy in this format, you only have one equation. You don't have to memorize any other equations. And this equation, you can write it out if you understand what my analogy with money. You don't even have to memorize, okay? So conservation of energy is simply saying energy final minus initial equals energy input minus energy output. And then when we actually solve problems, we just have to fill it, all these different energies. What is the final? What is the initial? And we put the quantities in. Of course, when you don't have any input or output, or in other words, when you don't have any transfer, nothing goes in or nothing comes out, then this part is zero, right? Zero on the zero input or output is really just, this is zero. Then your final and initial are equal, meaning that your energy in your system remains a constant. It does not change, but it's always conserved, right? Any kind of phenomenon, energy is always conserved, but it may not always be constant. Okay. All right, so simple enough, right? Let's see if we can use this to solve a problem, answer a question. Here I give you a question. We have a block and it travels with some initial velocity up a ramp, 40 degrees, and it has a total height of h. There's another identical block, travels up a ramp of only 20 degrees with the same initial speed. And how high would this second ramp block go in comparison to the first? All right. So I'll let you go ahead and vote on this. Okay, another 5 seconds. All right, let's take a look. This is our results. We kind of pretty much spread out between B, C, and D. So without us doing the calculation, I want to first show you guys a link for a demo.
Not going to be accounted for. So what I have in front of me is I have this track that these two endpoints are at the same height, but as you can see, the path at which to get to these two heights is different. So now I propose that since these are at the same height, using the conservation of energy, that if I start here and I let this ball go with its initial potential energy, it's allowed to roll down, get to the bottom, and only have kinetic energy. And with that kinetic energy, it's able to roll up, even though it's at a shorter path in terms of the X direction, but the same Y, that it should get relatively close to the same height at which it started. And by this, through the rule of conservation of energy, I can switch which spot I start first. So now do the experiment. I'm going to start here. As you can see, the first time we got relatively close to the original starting point. So let's do that one more time. Watch the ball. It got relatively close, probably within a diameter to a radius away of the ball itself. Now that's where we did not take friction into account, because we can also take a little bit of friction with this track right here, because it's maybe not perfectly smooth. Maybe if I took like some vegetable oil and I rubbed it down on this track, it might actually help it. But I'm not going to do that today. So now to do something similar, we'll start over here. So I'm going to guess that the ball should get to about where my finger is. I'm not going to move. I got a little bit shy of this. And as you can see, we can see the energy loss of the system, because the ball is not getting up as high as it initially was. And after some point, it's going to hit its inflection point, which is going to be at.
All right, getting back to our question, you can see this question is answered really well by the demo. Although in real life, we can never really have a frictionless surface. Here, we do not consider friction, no friction, right? So we do not consider the energy that's transferred into rubbing the surface into heat. So if that's the case, if you have some kind of kinetic energy to begin with, let's say you have 100 joules, for example, and all of that become gravitational potential energy at the top related to some height, right? If it have same amount of energy to begin with, of course, it's going to still end up with the exact same height as before. Even though you have a longer path, you're still going to have 100 joules at the top, right? So which will give you the same height for the second block. And for the next question, we're going to look at another demo that has to do with a loop-the-loop energy track. I'm sorry, loop-the-loop. Okay, all right, I'm going to go to the demo here.
This is a demonstration of a loop-the-loop, which you might encounter in some amusement park rides, et cetera, et cetera. The idea is you got a marble, you want to start it on this track, and you want it to get all the way around the loop-the-loop. We'll do the theory part of it in class. The experiment is kind of fun and interesting to watch. You start it too low, clearly doesn't make it around the loop-the-loop. If you start it at the height, roughly the same height as the height of the loop, it also does not make it all the way around. The reason is that if you start it here, conservation of energy says that whenever you get up to that same height, it's going to have zero velocity, because it had zero velocity when you released it here from rest. but you need it to have some velocity, and that velocity is the square root of g times r, g the acceleration of gravity. So it needs to be higher than that, and we'll work out the math in class. But clearly, if you're way up here and missed the track, sorry about that, makes it all the way around, and there's an intermediate spot here where it barely makes it around. I didn't quite make it there. And you saw in this particular case, I was pretty close to the threshold spot where I need to release it from in order to make it all the way around. What happened is it lost contact with the track up here at the top. You might have seen that in the video. And then it regained contact with the track after that. You definitely don't want to do that on an amusement park ride. That would be pretty scary. But on this, yeah, and so what you would have heard, you can hear the sound of the marble on the track as it's approaching the top, and then it gets very soft or disappears as it barely makes it around. If it's higher than the critical value, then you can hear the sound of the marble on the track the whole way around, if it hits the right track. Yeah, just like that. And the actual height.
Okay, so that's the demo. And the next few questions are related to the loop-loop. So let's look at this particular question, okay? Imagine you're designing this for a roller coaster. It was a marble in the demo, but we can view this as if you have a track that is moving along an amusement park, or using this as a model. So what would be the minimum height required for the object in the ball or the cart not to lose contact, not to fall off the track at the highest point at point B? Okay, so if you have a radius r for your loop and you can ignore air resistance and friction, well, it's just an approximation. In real life, you do have friction. Okay, so this is an example. It seems kind of, okay, so how do we get started? And I translated this to another question is, well, okay, if you have certain height, the ball will have different speed when you reach point B, right? So the way it is asking what is the minimum height is another way of asking is what is the minimum speed you need at point B, right? In order for the track not to fall off at point B. So if you figure out what the speed here is needed, we can go back to figure out what the height is at point A using conservation of energy. We have done a little bit of that already with vertical centripetal motion in our when we discuss Newton's laws. So that is this is another opportunity for us to revisit that particular question. So first of all, let's try to answer, figure out the situation of the free body diagram when the ball is at the top of the ramp. And then as the persons mentioned, the professor mentioned in the demo, there is a critical point, right? The ball is barely hanging out, barely going over. That critical point is what you mean by what is the minimum that we need, right? So what is a free body diagram of the ball at this critical moment? So I believe you have time. So I'm gonna let you discuss this with your group for a minute or two, and after you come back, you can vote. All right, just 5 more seconds. Okay, I'm gonna go ahead and close this. All right, so you can see the majority voted for C. That was the answer with the previous question was Newton's laws. Normally when we are having something going around the loop, right, we want to have centripetal force and we want to have gravity. Well, of course, we always have gravity, right? And you are also going to experience the normal force coming from the track, right? I think that's the 2 arrows. What I want to ask is, are we answering the same type of question here than before? Here it's asking, imagine the critical point. The ball is just barely going over without falling. So what does it mean, critical? When we say the ball is falling, meaning that it falls out of the track, it have lost contact, right? When you lost contact with the track, you're falling. So what is this critical point? You barely hang out. Remember the guy did the demo, he said, the critical point, you don't really hear much of the sound at the top. That means what force is really small or non-existent?
The normal force.
The normal force. So here, to find out the critical point, we need to set the normal force to be what?
0.
To be 0, yes. In real life, you never want that. You want it to be safe. But this is sort of a minimum, give you sort of an estimate of, well, that is barely making it over. So when you're barely making it over, you're only gonna have gravity. And normal force is 0 because you barely hang on, you have barely lost, you lost contact, right? Just the moment you lost contact, you barely hang on. So normal force is 0. So we should choose for D as the correct free body diagram for the critical point, only gravity. Okay, so now we have cleared out that hurdle. Now let's see if we can solve this problem together. Looks complicated, but we can do it. First question is, what is the minimum speed required for the ball not to fall off the track? Now we realize, okay, we have just said that the minimum is when f of g provides centripetal acceleration, right? So here, the free body diagram of the ball is really just gravity. So here, looking at point B, we're saying let's apply Newton's second law, F net equals ma on the track on the ball. The net force is only gravity, right? No normal force because this is the minimum. This is the critical point. So gravity equals ma. Now centripetal acceleration is what? V squared over r, remember? Okay, for circular motion. So your force of gravity is mg equals mv squared over r. So your v here is a minimum, right? It's the critical point. It's going to be square root of g times r. Okay, so the minimum speed required is simply this answer. You can plug in numbers, but I will hold off for plugging numbers until I get the answer for the next question. That's the minimum speed required. At this speed, at point B, you're barely hanging on. You have already lost contact. You're barely hanging on the track. Now, going back to the next question. Now you know the minimum speed. V here. Can you find out what is the minimum height required? Okay. Now here we use conservation of energy. So to use conservation of energy, I'm going to set up very similarly to how we demonstrated the conservation of money example. First, we wanted to establish our system. Okay. So what is system that you wanted to evaluate right now? You're interested in the motion of what object? the ball, right? So, okay, so I'm saying the system is the ball. But I probably want to consider a gravitational energy. That's why I should implicitly also add Earth. Okay, so I'm saying it's ball and the Earth system. Let's define a initial moment or initial state. Where do you want to start looking at the system? At what point? Initially, the ball is at which point? A or B or C or somewhere else? It's a process. The ball going from here to here, right? So during this process, initial state would be point A or point B or point C. Sorry. It would be point A, yes, point A. And final state is at point B because we have some critical information happening at point B. Then make sure to include that in your calculation. Final state as at point B. So from here to here, okay? Okay, so let's look at all the energies. What are your energy of the system at your initial state? Energy initial. So here, the ball is being released from point A. What kind of energy does your system have? There are only three types we talked about: kinetic, gravitational potential, and elastic potential. So right now, the ball and Earth system have what kind of energy? Do you think it has kinetic?
All gravitational potential.
All gravitational potential, very good. There's no rubber band, right? So no elastic. The ball is not moving, no kinetic. So just the gravitational potential, which is mgh. The height is what we want to solve for. Okay, what about the energy final? Final is at point B, final, right here. What kind of energy does the system have?
Both potential and kinetic.
A potential and kinetic, yes. Here we do have height. And how high are you above the ground? So let's set, this is our reference, like we measure our height. 2r, yes, your diameter, 2r. And also has some kinetic. The kinetic is 1/2 m v squared, right? That's the formula. V is the velocity at that point, and we're at point B, so it's velocity at point B, VB squared. So these two of them. Because we don't consider friction or anything else, your energy input, if you were have someone pushing it, or you have a power pushing it, but we don't have any of that. So that's 0. Energy output, you don't have friction, so you don't lose energy to your environment, that's 0 as well. Okay, so we have everything. And the physics we're going to use is conservation of energy. Conservation energy tells me E final minus E initial equals E input minus E output. So let's plug in these quantities one by one. E final, you got it here, right? MgA, sorry, these two combined. So final is, there are two terms, mg2r plus 1/2 mvb squared. Energy initial is just mgh. Input and output are both 0. So I got this. I can solve for height, right? So I can solve for height. And I also know VB. VB is calculated from previously here. This is VB, square root of GR. Let me plug that in. Okay, plug in minimum speed. So you have 2 mgr plus 1/2 m square root of GR squared equals mgh. Okay, so this is m cancels. This is 2gr plus 1/2 gr, right? Equals gh. Again, cancel g. So what is my h? H is 2r plus r over 2. I get 5/2 over r. That's your result. You can see the reason I keep my variable as it is to begin with, because you can eventually cancel a bunch of things and make your calculation relatively simple and avoid possible mistakes you might make along the way. So how high do you have to release the ball? If your radius is 5 meters, you need to release it from 5 or 2 times 5 meters. That is 12.5 meters above the ground to barely making it over. And that is not even considering friction. Now, if you have friction, you need to release it from even higher. Okay, so this is our very first application using energy conservation to solve. Looks like a complicated problem, but when you break it down, it's actually pretty straightforward if you figure out carefully what your energy is at the initial and the final state. Okay, any questions about this particular problem? Any questions about what I just did?
If the normal force wasn't 0, how would the problem work out?
If the normal force wasn't 0, then they must tell you something about, okay, you will have this kind of speed at the top. They will give you the speed. They'll tell you what the velocity is at the top, and figuring out, in order to have that speed, how high do you have to release it? That would be how it would go. And you can even, if they tell you the speed, you can even figure out how much is the normal force, right? Because if the normal force is not 0, you got normal force, you got gravity. Both of them provide centrifugal force. So normal force plus gravity is going to be ma, centrifugal acceleration. And the acceleration is related to the velocity at the top. If they tell you what the velocity at the top is, you can figure out how big of a normal force it is. Does that make sense?
Yes.
Yeah. So yeah, that's a very good question. That sometimes you could have a variation of the problem given to you that way. Or they might tell you the height and tell you to find the speed here at this location. Or they may even tell you to find the speed at point C or some other random point, which will be, again, an application of conservation of energy. And you can go home and try to say, okay, if I were given this height, can I figure out where the speed is at point C? Right, C has a different height above the ground, is radius r. So can you find the speed at point C? That's something you're totally prepared now to answer. Okay. All right, so that's all we're going to do for today. We'll spend next couple weeks talking about energy again, the work, those concepts. But our exam will be focused on kinematics and dynamics, which are ends at Newton's third law. So I want to remind you, it will be available on Blackboard starting the midnight of March 9th, Tuesday, and will be there until 11:59 p.m. of that same day. So you can pick any 2-hour period to do it. I believe someone asked me to be present, open up my class Zoom in case you want to ask questions, and I will make sure to have my classroom open. But we will not meet on Tuesday, okay? We're not gonna meet that day. You're just gonna have to find time to do your exam online, okay? All right, if you continue to have questions regarding preparation of exam over the next few days, feel free to email it to me. I will get it back to you guys, okay? All right, I'll see you. Well, I don't see you. If I don't see you next Tuesday, I'll see you on Thursday, all right?
Bye,
Thank you.
Professor.
Bye.
Thank you, Professor. Have a great
Thank you,
week.
Professor.
Thank you. Have a good day.
Thank you.
The exam is not curved to answer the question, but I do curve the final grade if necessary. Okay, no problem.